Okay, in this lecture, we're going to be going over the paired samples t-test example for the final project. So I'm going to go ahead and share my screen. So this right here is the example file, and you should have all of this wonderful information here. We have um, the data right here. It says basically, let's take a look at what we're doing. This yellow box right here gives you a some information about, hey, this is what it is that you're looking at. The data allows you to explore the average difference between the speed dependent on the independent category 1 backwards car speed paired with the speed dependent on independent category 2 forward car speed. The speed dependent uh, on backwards car speed are paired with the specific speed dependent on the forward car speed on car. And just so you know, all of this is just a big formula. So you can kind of see, if you look at this, it's like, oh, it tells you what all these different things are if you're wondering why it's really clunky. But basically what we have is we have the backwards car speed and the forwards car speed, and it's paired on each individual car. So we have all of these different cars, and we have the speed that they were at going backwards and the speed that they were at going forward. So sad story. The story is that I actually did a whole bunch of work putting this all together, getting all this super cool data together, and then I lost it all. And I had to redo everything. So there's some of the information that you have in front of you, I had to redo it, but that's what all of this information is right here. And I'm going to show you something. Let's see here. I'm going to see here, links. Okay, so this right here is a bunch of, let's actually get rid of a few more. This is a bunch of different cars, right? And so I have all these different cars right here, and I raced all of these cars backwards and forwards. And when I raced them backwards, they had one time, and when I raced them forward, they had another time, or they had a different speed. And so the question is when we race these cars forward, do they have a different speed as compared to when we race these cars backward? And you can see right here, here are some of the cars that we have. Let's see here. I'm going to, oh, there we go. So we've got, I didn't mean to actually click on it, but we have the, this right here is the, I'm not sure what these cars are. I think that looks like a Viper. Uh, and so we've got all sorts of different cars that we let race around the track. And then we took their speed going backwards and forward. Okay, so looking at this, we have the backwards car speed and the forward car speed. So let's look at the prompt. It's the age-old question for Hot Wheels cars. Do cars run at a different speed depending on whether they are run backwards or forwards? A random sample of 27 cars was taken by running the cars on the track forward and backward. The speed of the cars at the end of the lap were recorded to determine if the cars ran at different speeds depending on the orientation of the car. Can I be 90% confident that cars running backward will be slower than cars running forward? So, the question is, the research question, if you will, is can I be 90% confident that cars running backwards will be slower than cars running forward? And this is really important because we need to ask ourselves, is this an upper tail test, a lower tail test, or a two-tail test? And this will be when we're comparing the cars running backwards to cars running forward. And when we say that the cars running backwards will be slower, that means that it's going to be a lower tail test. So we think that the cars running backwards will be slower than the cars running forward. Next, let's go ahead and take a look at this. What is the dependent variable? So the dependent variable is car speed. Which I actually have that right up here. But the reason why it's car speed is because the speed of the car is dependent on whether or not it is running forward or backward. Next, what is the independent variable? In other words, what is the dependent variable dependent on? And that is the orientation of the car. In other words, if it's facing one way, it's going to be going a certain speed as compared to the other way, it's going to be going a different speed. And then what type of data is the independent variable? And that is nominal. You could make the argument that it is ordinal because you can put them in order. Backwards is going one direction, forwards is going the other direction. But it's really just two categories, and it really doesn't matter all too much. Then what are you examining or comparing? And once again, go back to the paired reference, take a look at these right up here, and you are going to choose one of these and modify it for what it is that you're doing. So determine if there's changes over time. No, not that. Determine if there's differences between conditions. That's a possibility. Determine if there's a difference between measurements. Determine if there's difference between matched pairs. And this is what we're looking at. The conditions are is one's moving forward, one's moving backward. And so we're looking at the difference between conditions. So determine if there are differences in car speed between conditions of cars either running backwards or forwards through the track. Then what is the tail of the test? This is going to be a lower tail test, like what we said earlier. And then also what type of test are you conducting? And that's paired samples. And I want to go through this really quick. This is the decision tree, and I'd highly suggest that you familiarize yourself with this decision tree over and over and over again with everything that you're doing. But we've got continuous data or frequencies. Are we counting or are we looking at continuous data? And we're not counting observations. We are comparing the means of two different groups, if you will. So are you examining the difference between a sample and a population, or are you examining the difference between groups? And we are examining the difference between groups. And then any of the following, are any of the following true? Are the same subjects being tested more than once? Well, let's keep going. Do you have two or more scores on the same dependent variable for each subject? Or are you examining the difference within each individual subject? And so the thing that we have is we have the subjects being tested more than once. And we have them tested once going forward, or sorry, once going backwards and once going forward. And so the answer is yes, which brings us to within subject design, which you don't have to necessarily know what that, but basically you're saying we're looking at the conditions within a whole bunch of individual subjects, and we are looking at two different groups, one going backward, one going forward. Therefore, we are going to be running a paired samples t-test. And this is how, a simple 6-step process of running a paired sample t-test to get the t-value, the t-score right down there. So let's look at this paired. So what type of test are you conducting? And it's paired samples. And then the null and alternative hypothesis, once again, come right here. And this is the example of how we write the null and alternative hypothesis when we have a paired sample. And the reason why we have it run like this is because we're not actually comparing the mean of the backwards cars to the mean of the forward car. What we're looking at is just one value. We are looking at the different scores of each one of these. So this car, this aqua green F prototype project 71, let's see here. I can grab this car really quick. So we've got this car, and it is right here. And this car going backwards went 75 miles an hour, but going forward it was 81 miles an hour. So that means that it had a difference of 6 let's see here, equals 75. Yeah, should be equals, I don't know why all of those scores are definitely wrong. Yeah, a difference of 6 miles per hour. And I need to bring these all the way down. I think I just forgot to redo that. But anyway, so it has a difference of 6 miles per hour slower. This one, Black Drifta 1, this is going forward, it was 5 miles an hour faster. The Black GT3 Vantage 1 was 52 miles an hour slower when it went forward, or sorry, faster when it went forward. And so we have a difference score calculated for all of these. And so really what we're looking at for more than anything is just the difference score, which it appears to me that I definitely need to redo pretty much, well, just this, and you'll see why. But so we are actually comparing the difference scores, and we're wondering the average of all of the different scores. So I'm going to show you the average of the different scores equals average of the different scores is 0.2962. In other words, the cars running backwards were 0.2962 miles per hour at scale faster than the cars running forward. So they were slightly faster, but once again, we're doing hypothesis testing to see if does that actually even matter. So next we have this right here. So the mean difference. This is saying the null hypothesis is that the mean difference is greater than or equal to 0, and the alternative hypothesis says the mean difference is less than 0. So in other words, the backwards track time is going to be slower than the forward track time. Next, what is a level of significance? And that is 0.1 because we've got a 90%, can I be 90% confident? What is the test statistic? And we're going to go with T. And what I want you guys to do is, if you know the population standard deviation, then go with a Z. If not, just always go with a T. If you only know the sample standard deviation, just go with a T. What are the degrees of freedom? And I know that I may have said something slightly different earlier, and I think what I've gone with earlier just makes things a little bit more confusing and just adds a whole bunch of rules for things that don't really even need rules. So what are the degrees of freedom? The degrees of freedom is going to be the number of difference scores minus 1. So there's a total of 27 difference scores here. So 27 difference scores minus 1. So that is going to be a total of 26. And then what are the critical values? So great, there's an easier way to do this. Okay, so we could calculate the critical values, which really wouldn't be too hard, or we would just go to a t-chart, or we can do data. Let's do data analysis, and we are going to do t-test paired sample 2 for the mean. And so I'm going to do variable 1, cars running backwards, and variable 2, cars running forward. And we have labels up at the top, and then I'm going to do an alpha of 0.1, and then I'm going to put the output range right here. So I did the output range right there, and once again the alpha of 0.1 because we have we want to be 90% confident, so the alpha is 0.1, and then press OK, and then you'll see, okay, we've got the T critical for a 2-tailed test and the T critical for a 1-tailed test, and bada bing, bada boom, it's right there. So you can literally just copy and paste this in there, and it gives you the T critical for a 1-tailed test. However, this answer is actually wrong. And the reason why it's wrong is because this tool will always give you a positive number. When we're doing a lower tail test, you've got to change that to a negative. So change that to a negative. It doesn't differentiate between 1-tail positive, 1-tail lower, or 1-tail negative. So you've got to do a 1-tail, you've got to change it to negative. So we're going to do negative 1.3497, and I'm going to come right back up here and make sure that it is negative 1.315. Next, are any assumptions violated? In order to do this, the first thing that we need to do is we're going to run the descriptive analysis or the descriptive statistics tool. So we're going to do data analysis, and then we're going to do, let's see here, descriptive statistics. Press OK. input range, and we are going to highlight all of these values right here. And I'm going to do output range, and I'm going to put it right here. Summary statistics, confidence level, once again, we'll do 90. And press, yep, press OK. Oh, and labels in the first row. When it says non-numeric, make sure that you have the labels in the first row, and then it just overwrote all that. So we're good to go. And you'll notice that all of the descriptive statistics for the backwards car speed, the forwards car speed, and the difference scores are all right here. So the only thing that we're really looking at is the difference scores. And we're going to have to actually redo some of the things that I wrote right over here. And the reason why is because I accidentally did the difference scores based on a different set of data. I did it, I just forgot to redo the values. So don't do that. Don't forget to redo the values and put your own values in there. Don't use somebody else's values. So are any assumptions violated? So we're going to go to the paired reference and we're going to look at these assumptions. There's one dependent variable that's measured at the continuous level. Okay, so is there one dependent variable measured at the continuous level? Yes. Car speed is that dependent variable. Next, one independent variable that consists of two categories and the car orientation. This is the independent variable and it's got two categories, so that's good. Next, there should be no significant outliers. Okay, so and that's in the difference score. No significant outliers in the difference score. So we're going to look at outliers. In order to do that, we are going to look at this. Different scores, and we've got to redo this now. There is one outlier above, most likely. We'll take a look at this at 43, and one outlier below at negative 52. Okay, and then we have the let's just finish this really quick. Although let me show you really quick how to do this. The difference score. So we're going to highlight the difference score, and then we're going to do insert chart box and whisker, and then you can modify this. Double click on it, and then add chart element, data labels to the left, and then make sure that you give it a title, so on and so forth. Okay, so any value above 34 or below negative 36 are outliers. So I'm going to do something really quick, and I am going to, let's see here, sort filter, sort smallest to largest. I don't know why. Negatives, oh, I know why. Because it treated this like the label. So let's try that again. Filter, smallest to largest. There we go. So anything below negative 36, so that's just this black vantage, and anything above 34, if I'm not mistaken, let's just come over here and make sure. Yep, anything above 34 are outliers. And so looking over here, 34, there's only one above and there's only one below. So there's only a total of two outliers. So one outlier above and one outlier below. So max value that is not an outlier, that's going to be 34. Q3 is going to be 10. Then the median is 1. And then I'm going to zoom in to find the mean. The mean is 0.296. So the mean is 0.296. And then Q1 is negative 10. And then min value that's not an outlier is negative 36. And then number of outliers below is one outlier below at negative 52. And then once again, we've got the histogram, which you guys know how to make histograms. So let's see here. There are any assumptions violated? one outlier above and one outlier below, but no other assumptions violated. Now, the nice thing about one outlier above and one outlier below is you look at the skewness and kurtosis here, and there's virtually nothing wrong with this data. It is very like normally distributed. And if I could probably play around with this chart a little bit more, but the distribution is actually a really good distribution. Okay, so what is the calculated value of the test statistic? Coming right over here, let's take a look at this test statistic. You just look at the t-test paired sample, and you'll see, okay, t-stat is right here, 0.07104. So then we take that, put it right over here, 0.07104, determined by the data analysis tool for paired samples t-test. What is it calculated value? In other words, it is 0.07 standard deviations above the mean. Next, what is the probability? So the difference score, it's actually point above 0, 0.07104 standard deviations above 0. Next, what is the probability of an observation of observing a sample value as extreme as or more extreme than the value observed given the null hypothesis is true? The probability of getting something more extreme than this is just a little over 50%, or just a little under 50%. It is 0.4719 ... And so in other words, it's almost 50% probability that we would get something more extreme than this, assuming that that there is no difference between running a car forward or back. Next, or that a car does not run faster or does not run slower. Yeah, that there's no difference. Let's just stick with that. All right, next, what is your decision? We failed to reject the null hypothesis, and the reason why is because this p-value would need to be less than 0.1, or this calculated value would need to be greater than point would need to be greater than, or sorry, less than 1.315. So it would need to be less than this, or this would be need to be less than 0.1. So failed to reject the null hypothesis. And then what's the margin of error? So this, once again, I've got to redo. The margin of error is right here. So we're just going to Control C, and we're going to put it right there. So the margin of error, we are 90% confident that the actual mean difference is, so put the mean in there, 0.2962. Okay, so let's do 0.2962 plus or minus 7.113 plus or minus 7.11, let's do 4, because 7.1137, so 7.114. Or if you actually do the math, let's do the mean, which is 0.2963, and then equals the mean minus the margin of error, and then equals the mean plus the margin of error. And so if you wanted to actually put the range in there, you would put or between negative 6.8175 and 7.4107. Okay, so what I put in there is basically we're 90% confident that the actual mean difference is 0.2962 plus or minus 7.114, or I put the actual confidence interval in there. Then what's the effect size? Once again, I've got to redo this one over here, but let's take a look at the effect size, how to calculate the effect size. So we're going to look at the effect size right here. It's the mean divided by the standard deviation. So we're going to do the mean. So what is the mean? The mean is 0.2962. So we've got that 0.2962 divided by the standard deviation, which is 21.67. Okay. Which gives us an effect size of 0.0136. And if we look at the this this interpretation, the effect size is 0.01. In other words, it is tiny. And so the way that I calculated it before, just ignore that. So I'm gonna get rid of that and just put it right here. And so if we had a significant result, the effect it would yield a very small effect size. You would need a very large sample size to be able to see a difference or be able to observe a difference. Okay. And that's what an effect size is. In other words, you can't really see the difference at all. There is virtually no difference between running a car forwards or backwards based on the data that we have. Okay, next, we're coming down here and we're saying what was run. A paired sample t-test was run, comparing what. You know, you can just come right up here, copy and paste. What are you doing to determine the difference between car speeds condition running forward or backwards? What was the result? The average difference in the speed running the car back, forward or backwards is, let's do, is, see, I messed up one little thing and it messed everything up. So don't mess up that one little thing. 2962. The probability of getting this result, assuming there's no difference in speed between the two groups, is about 47% or 47 or 0.47195, which once again, I just took the p-value right here. You can literally just copy and paste this. The probability of getting these results, assuming that there's no difference between the groups, is, and then just put your information right there. It appears as though there really is not much of a difference between running the cars forward and backwards, which is the insight about the possible factors. I mean, it's not even about sample size at this point. Even if you had a massive sample size, there's really nothing there that tells us that there is any difference at all between running cars forwards and backwards. Then we are 90% confident that the actual mean difference is, which once again, we need to just copy this, the margin of error. Okay, so we are 90% confident that the actual here, let's do this. Yep. We are 90% confident that the actual mean difference is blank or between blank and blank. And then you can put mean difference between running the cars backwards and forwards. It's so easy to just assume that people are right on board with you with everything that you're saying, but make sure that you write what it is that you're saying. Like, and I know that I'm really bad about that. So it's something that I've got to work on too, but make sure that you write the actual mean difference between running the actual mean difference between running of the speed of the cars between running the cars backwards and forwards is 0.2962 plus or minus 7.114, or between blank and blank. Okay. then how should these results be used? The present results should not be used to indicate any difference between running the cars forwards or backwards. And so you guys have your own data sets as well, and you should be able to take this and interpret your data sets and along with the other stuff that you have, the other lectures that you have, and should be able to help you to do great. So hope this was beneficial to you, and yeah.